Hello everyone, my name is Pawan Toki and today I'll be talking about 3D integrated circuits. So let's get started. This is the flow of presentation and we'll be acquainted with the topic and then excavate the different facets of 3D integrated circuits. Over the last few years, we have seen tremendous logical and economic progress in semiconductors and microelectronics, following what is known as Moore's law. According to Moore's law, every 2 years now, amount of transistors we can integrate on a IC doubles. This exponential increase in integration is achieved by scaling down the dimensions of microcircuit by a factor of zero point 0.7 and every technological node. For most of that half century, the scaling was relatively easy and was associated with about 30% reduction of transistor cost, a greatly improved performance and marked reduced power consumptions. However, recently the trend has changed dramatically and it is now harder technical and leave both to achieve dimensional scaling. As a result, there are dimensioning improvements in transistor cost power or performance or new form of scaling is shaping up as an alternative to maintain the exponential increase in integration. This new form of scaling up is 3D integrated circuits. 3D integrated circuit is built by vertically stacking different chips or wafers together into a single package. Within the package, the device is interconnected through Silicon Valley wires or hybrid bonding. Now, let's talk about the motivation of 3D IC. With a huge demand of data compute, allowing more processing in a tiny area at a low power is a must. By contrast, for 2D designs, more processing means an increase in chip area and power. 3D designs or vertical integrations have emerged as viable solutions. A 3D IC architecture increases functional density at the same or reduced power keeping the same or smaller area. This results in a smaller package for electronic devices. So this slide shows a brief flow and the comparison between 2D and 3D ICs. 3D ICs provide higher speed and small footprint than the one designed by the traditional 2D design technologies, where the length of the global wires can be reduced by as much as 50%, and the limited clock frequency can be increased and the limited area and power can be reduced. Now, the technologies that we use to build 3D ICs. First, wafer to wafer. This approach involves stacking multiple wafers of components vertically, typically TSVs or other bonding techniques. Electronic components are built on two or more semiconductor wafers in this technique. This integration can be used to scale up production and can be used to integrate components manufactured using different processes. Chip to chip. Electronic components for these techniques are built on multiple chips. In this approach, multiple die or chips are stacked vertically using TSVs or other interconnect techniques. This approach is often used to stacking memory on the top of logic chip to improve performance. Chip to wafer. Electronic components are built on two different semiconductor wafers. In this approach, individual chips are embedded in wafer and the wafer is then processed to create TSVs or other interconnects between the chips. This approach can be used to combine chip manufactured using different processes, allowing for greater design flexibility. This image shows different integration or technologies used to build 3D ICs that we talked about in previous slides. Monolithic ICs. Electronic components, example transistors, and their connections are built on single silicon wafer, which is then diced into 3D ICs. Monolithic 3D ICs are theoretically one of the most attractive options available because they allow for very short and fine pitch wise, thus reducing the interconnect parasitic considerably. Due to the usage of only one substrate, there is no need of alignment, bonding, thinning, or TSVs. It is mainly uses monolithic inter-tier wires. These 3D ICs have potential to make seamless communication between the different layers of 3D IC a reality. The most common study architectures for 3D ICs. First, silicon interposer. Silicon interposer technically not a true 3D architecture. It provides several advantages over conventional packages. First, very fine wires, pitch wires, similar to on-chip interconnects can be patterned on silicon interposer. Secondly, silicon interposers offer significant bandwidth and energy improvements over conventional off-chip interconnects. Stacked memory. It is a multiple DRAM die that are stacked on top of each other with one logic die at the bottom for control. The memory stack significantly increases the capacity that can be fit in a given area, whereas the logic die handles communication with other ICs on the interprocessor. Memory on processor architecture. This, this has the ability to stack high density DRAM on top of the processor, which is extremely valuable for applications. By minimizing the physical distance between the two communicating ICs, the losses in the chip-to-chip leap can be minimized. Logic and logic architecture. The motivation for stacking logic on logic is to reduce the aggregate interconnect length in a large logic circuit. For example, if a large 2D chip like a microprocessor is 2 by 2 centimeters in dimensions, the overall interconnect length can be reduced significantly if the microprocessor is partitioned into 4 blocks of 1 by 1 centimeter stacked on top of each other and connected with TSVs. Heterogeneous integration. This is the ultimate holy grail for researchers seeking to integrate multiple technologies stacked together in a single package. The dream is to one day combine logic, memory, RF sensors, ICs, built separately in an optimal technology within a package. There are several advantages to such a heterogeneous 3D ICs, including cost, form factor, performance, IO connect reductions, and lower power consumptions. So, advantages of 3D ICs. So, 3D ICs offer low cost and the footprint more functionality fits into small spaces. This extends Moore's law and enables new generation of tiny but powerful devices. Heterogeneous integration. The circuit layers can be built with different processes or even on different types of wafers. This means that components can be optimized to much greater degree than if were built together on a single chip. It offers higher power. Keeping a small on-chip can reduce its power consumption by 10 to 100 times. Shorter wires also reduce power consumption by producing less parasitic capacitance. 3D ICs also offer lower bandwidth. 3D integration allows large number of vertical wires between the layers. This allows constructions of wide bandwidth buses between functional blocks in different layers. 3D ICs also have shorter interconnects. Now, we'll see the challenges that 3D ICs offer. First one is heat removal. The performance of modern electronic chips is primarily limited by their power consumption and the effectiveness of cooling systems. 3D integrations makes heat removal harder because the hotspots on the die further away from the heatsink are not easily accessible. Next, IC testing and yield. This is another crucial challenge that impedes the widespread of adoption of 3D ICs, which is the problem of testing. Although it is desirable that only known good die are handpicked from the wafer level testing and stacked with KGD to form different layers of 3D ICs, it is extremely expensive to assemble 3D ICs at the die level. On the other hand, wafer level assembly is cheaper but leads to a significant yield loss. Power delivery. Power is delivered to a die higher up in the stack through power ground TSVs that need to distribute it over the area of the die. Since the performance of each die in the 3D IC is a strong function of the I drop, a significant number of TSVs need to be dedicated to power or ground TSVs. Taking full advantage of 3D integration requires sophisticated design and techniques and new CAD tools. Reliability. Depending on the process used for TSV fabrication, the reliability of transistors or interconnects on the chip can be severely impacted. 3D ICs have many applications in the field of electronics and computing. Following are some applications of 3D ICs. CMOS image sensors, pixel array for particle detections, 3D stack memory, multi-core processors, micro displays, and network on chip. So, to conclude, this was a brief overview on 3D integrated circuit technologies, architectures, ways of integrating, advantages, and challenges. 3D IC design is a relief to interconnect driven IC design. Overall, 3D integration is a significant development which has major impact on how future electronic systems are designed and used. Thank you.